Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Continue to the BJT as analysis. In this moment, I will talk about the two-port system approach for the BJT as analysis. Why this is important? Because if we connect the amplifier as like a cascade. Cascade is means like a series amplifier. We have a 3 amplifier, and we connected in a series. We have to calculate the total gain of the amplifier of the system of the amplifier system. So it is very easy for us if we look the single of the amplifier as a two-port system. So we have like a 3 amplifier, so we have 3 two-port system, and then for cascade we only have to multiply each the gain of the two-port system as a whole of the total gain of the amplifier. So in this subchapter, I will look for the two-port system approach, how to calculate the gain non-load voltage gain, and then also full load voltage gain. Okay, the first one, look at the picture. We have the two-port system here. This is the transistor. So this is the transistor, and then we draw in the two-port, and we have the AVNL. AVNL is the voltage gain no load. So in this in this transistor, we didn't connect any load in the transistor. So if we take a Thevenin look, so this is the Thevenin look at the output of terminal, and I suppose you already know about the two-port system in the electric circuits, I think. So if we take a Thevenin look at the output terminal, we find that Vi here, the input, is set to 0. So the Vi is set to the 0. So we got that the Thevenin is equal to ZO in the output is equal to RO. Okay, RO is the output resistance of the transistor. And then in the Thevenin look, so we can write that E Thevenin is equal to VO. So this is the output voltage is equal to E Thevenins. And then we got that AVNL, the voltage gain no load, is VO per VI. Okay. So the VO is equal to AVNL dot VI. Okay. So A Thevenin, because it's equal to 0, is AVNL. AVNL is voltage gain no load, so we didn't connect that load in the this transistor as I say before, so it's equal to like this one. A Thevenin is equal to AVNL dot VI. Okay, so if we draw this two-port terminal with the AC analysis model, so we can draw like this one. Okay. So this is the connected to the ground, and then we have the input resistor here, and then we have the gain AVNL dot VI here, and then we have the output resistor here, and then we have the output voltage here. We have the output current, and we have the input current here. Okay, I forgot to explain here. If we connected, if we look at the Thevenin loop in the output, so we can determine that in the input port, the Zi or input impedance here is equal to Ri. Ri is input resistor. Okay, and then we using this input resistor as the input impedance. Okay, so in this BJT analysis, we can see that both of the input impedance, I and ZO here, is determined only in the resistive element, the input resistor and the output resistor. This is the simplified model in the BJT. Actually, if we look at the BJT analysis, we have to calculate another impedance like a capacitor and inductive element. But here, for the simplify, we only calculate the input resistance as the input and the output impedance. Okay, so if we draw in this circuit, this is the two-port element. This is the two-port element here. Okay, so this is the two-port element here. So we can represent like this one. So okay, and then from here we see that we can calculate the VO. VO is this one, the VO. So the VO, okay, VO is equal to FVNL.VI. Okay, FVNL is the voltage gain no load dot VI, and then here we can also determine the AI current gain is equal to minus AV dot ZI per RL. Okay, AV is voltage gain, ZI is impedance, and RL is load resistor. If we define the load for this consideration, but if we didn't connect it to the load, so the AI is equal to 0. It's like if we connect, it's no load. We didn't connect any load in the output terminal, so the output terminal is open. So the I/O is equal to 0. So if the no load, so the I/O is equal to 0. So it means that the AI is also equal to 0 here. But if we connect to the load, we can get that AI is determined by ZI and also the RL. So if we connect this output terminal with the load here, so we connect it to the load, so the RL is load here. So we have to, in here we have to make, before is if no load, VO is equal to a VNL.VI, but if we connect the load here, so it's become the voltage divider, because of if we want to calculate the VO here, VO is parallel to the RL, so the VO is equal to VRL here. This is the parallel connection. This is the VO and this is the RL, so this is the parallel connection. So the VO is VRL. So we have to calculate the voltage divider in this case, because we have two resistors here. The first one is RL and another one is RO here, and then we have the input voltage, or our input source is AVNL.VI here. Okay, so by using the voltage divider, the VO is equal to the VRL is the RL dot AVNL dot VI per RL plus RO. Okay, so the AV here is VO per VI, so it's equal to RL per RL plus RO dot AVNL. Okay, so we know the connection between the AV and AVNL. So this is the AV, the voltage gain if we connect it to the load, and this is the AVNL if no load. So AVNL dot RL plus RO is the total voltage gain if we connect it to the load. So this is the ratio of the RL and RL plus RO is very important here. Okay, so now we determine the AI. AI is the IO per IE is equal to minus VO per RL for the output, and for the input is VI per IE. So it's equal to minus VO per VI dot ZI per RL. So we got that AI is minus VO per VI is AV dot ZI per RL. So this is the AI. This is the current gain. Okay. Okay, so I think this is the final for the first part of this two-ports approach, and we already know about the AV, the voltage gain, and then AVNL, voltage gain no load, and also the AI, and how to draw the connection between the AV and AI. Okay, we will continue the part 2. Thank you very much for your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.